In our second episode, again, we're going to be discussing combinational logic, and we're going to pick up the discussion here as we think about module instantiation. So if you would follow me to the ebook, and let's take a little bit more time to understand what module instantiation is and how it works. Again, the core concept is we create some module, for example, the half adder shown here, and then we can simply, here's our half adder, and then we can treat that as a box and instantiate or stamp that into our design. So you can see in the resulting design, we've put in two half adders, taken the module we defined earlier and used it twice. And the only real challenge is how to match up names between an external port, such as an input B coming into the design, and the name of the port on the module that we're instantiating. And you can see the appropriate syntax here. We always first talk about the name of the port on the module we're instantiating, and then the name of the signal, wire, input, output, whatever connected to that port. As long as you keep that order in mind, we're always going to talk about module first and then what's connected to the module second. You'll find the ordering to be fairly natural. I did want to again emphasize and call out the use of local variables. We've, for example, defined a half adder one sum variable and use that to connect one half adder to the other. And in particular, you see that connection right here as we connect the sum output of half adder 1 to the B input of half adder 2. So that would imply we have two different connections. You can see the first connection here where we define the sum output of half adder 1. It's connected to this half adder 1 sum. It's not shown being named here in the schematic, but this is the appropriate name in the resulting module. And then that's going to be connected to the B input of our second half adder, which you can see right here at the bottom of the screen. The combination of local variables with modules allows us to provide a lot of flexible and useful connections. Again, make sure you understand the ordering. We're always going to go from the module itself that we're instantiating, the names or ports of that module, and then talk about the names of external connections, whether they be external to the module in which we're instantiating or just a variable such as that half adder 1 sum, a local variable in the module. Notice also, as we go to the next page in the example, the first instantiation for this particular example is provided for you. Again, here's the name of the port A. This, of course, refers to the port on the module we're instantiating. And second, the name of that in the external world, here, one of our inputs. That becomes a bit more clear when we think about the output. The output of this module is called correlation, and you can see the output of the module, that is the correlation, is connected to the AB correlation output in the larger context of where it gets instantiated. Again, just as long as you think of name of the instantiated module port and then the thing it gets connected to, the ordering is fairly straightforward. Let's continue to the next page where we look at conditional operators. Again, the conditional operator is the combination of a question mark colon. It's essentially an if statement that's an expression. In other words, we're given some condition that's true or false, and it could be a simple variable. Remember last time when we looked at assigning a relational expression to a variable, and specifically that was in operators ex4. So for example, we have the value is less, and we can use that. I'm going to go back a link. We could use that as our condition, that variable is less, or an expression like value less than 5. Either one is acceptable as a condition for our conditional operator. And remember, the conditional operator is an if statement that's been compacted into a single line. If the condition is true, then the result is this true expression. If it's false, the result is a false expression, which again gives us the ability to create a mux, a multiplexer, something that routes. In this case, we've got a final blower speed. If our blower is enabled, that's the is enabled variable, a 1 or a 0, a true or false value. If that's true, then we send blower speed through. You can see is enabled acts as a select to the mux. If the select is a 1, and you can see s equal 1 for the select input, then blower speed is routed directly through the mux and makes that nice connection from the input of the mux to the output of the mux. In contrast, if the is enabled variable is false, then we would take the false value, which is a set of zeros. And again, the zeros in this design are represented using a ground. And that ground is simply transported through our mux when the select input is a 0. Again, you can see s equal default, which in this case is a 0, passing that data through our mux. The conditional operator is great syntax. Make sure that you're comfortable with it. We'll find that it comes in handy again and again. Again, just to illustrate this concept, let's look one more time at the resulting mux we've inferred, that is, that we've caused Verilog to create based on this expression. We have an output value x. Our condition is C. So C is the select value for the mux. If C is true, then we can see that the B input, the true input, is routed through. If C is false, on the other hand, then we can see that the A input, when select is 0, gets routed through our mux. Now let's look at applying that by going to the next exercise in the series. Notice our strategy. We need to compute two things. First of all, a single bit variable called carry in. This is a great opportunity to use an expression like raw sum greater than 9. If raw sum is greater than 9 in a BCD adder, that means that we've produced a carry. Any number that's greater than 9 is a carry when we're representing binary numbers in this decimal format. So we can simply assign that to a single variable, just as we've discussed earlier in this operators EX4 exercise. But this is not where we're going to use the conditional operator. We're going to save that for the next line. If carry out is true, we produce raw sum minus 10. Otherwise, we produce raw sum, and then we simply assign that to the sum value. Make sure that you're comfortable using these conditional operators. They're extremely effective and efficient ways to express hardware devices like a mux. Now that we've covered the mux in some detail, in the next video, let's discuss creating larger muxes and adding a bit more language capability using the case statement.